talking about wavelengths between 400 nanometers and 2500 nanometers, or 0.4 microns and 2.5 microns, right? And as we went through that kind of performance modeling exercise last week, when I gave you those toolbox equations, and you remember we worked out the amount of energy that came from the sun, the amount of energy which arrived at the Earth's surface, at the top of the Earth's atmosphere, the amount of energy that made its way down to the Earth's surface having passed through Earth's atmosphere. And when we got to that stage of the calculations, we could easily see from the plots that basically not much energy beyond 3 microns makes it to the Earth's surface, right? Therefore, the Earth doesn't reflect much light beyond 3 microns. Most of the energy it reflects is the 0.4 to 2.5 micron region, which is why that's the region we call the V-square region, and is predominantly the domain of reflectance spectroscopy. As I mentioned, and I'll show the graphic again, if you use photons of higher energy, you probe electrons which are closest to the nucleus, because those electrons are more tightly bound, and in order to get them to perform a quantum leap from one energy level to the next, you have to provide more energy because you're doing more work against the attractive force of the nucleus, right? So in the kind of gamma ray spectroscopy stuff that Peter's been talking about, you are looking at electrons which are real close to the nucleus. In the kind of remote sensing that I've been talking about, we're looking at valence shell electrons, so the most easily displaced electrons, the ones which are part of an atom, part of an ion, but they're relatively far from the nucleus, and they're also shielded from their nucleus by other electrons, which means it's relatively easy to boost them out. And photons of visible and shortwave infrared wavelengths have enough energy to cause those electrons to be displaced, right? And therefore provoke an absorption. Right? When we go to the thermal infrared part of the spectrum, the photons are of lower energy, right? So you remember the plot I showed you in like the first time we got together, and I showed you wavelength against frequency against photon energy. And as the wavelength of the light increases, the frequency of the light decreases, and the energy each of those photons carries decreases. And I showed you the simple equations that you could use to work that out. Right? You could work out the number of the joules of energy in a thermal infrared photon versus an X-ray photon. What that means is that if we study planetary surfaces in the thermal infrared, we're looking at how longer wavelength, lower energy photons interact with matter, and therefore we're looking at a different aspect of matter. We're looking more at the bonds between ions rather than the ions themselves. Right? And the bonds themselves are interesting. Right? I'll show you a graph at the end of this slide set. Silicate minerals are the most dominant type of minerals in the solar system, in the inner solar system. And it's quite easy to distinguish fundamental types of silicate minerals, and therefore the rocks that make them, on the basis of their long-wave infrared emission signature. Because the primary difference isn't so much what they contain, it's the way the silicon dioxide sand, I mean the sand here is calcite, right, not silicon dioxide. But if you go to a place on the mainland, you'll see sand beaches. The silicon dioxide or the silica is bonded in different ways, and it's the bonding which really tells us the difference between rocks rather than what they're made of themselves. And in the visible part of the spectrum, that's invisible to us, because visible reflectance and shortwave reflectance doesn't tell us about the bonding of those rocks and minerals, but long-wave reflectance does. So we're going to talk about thermal remote sensing today. We're going to talk about how it can be used kind of like emission reflectance spectroscopy to chemically fingerprint targets on planetary surfaces. And as I said, we're doing this because it tells us something different about those materials. We're also going to talk about how we can use these measurements to work out something about the physical composition, or how the matter is put together. So are we looking at rocks which are solid rocks, or are we looking at rocks which are rocks that have been ground up into granular media or powders? We can use thermal remote sensing to work that out. We can also use thermal remote sensing just to work out the temperature of targets, right? And that's just a simple extension of the kind of Planck's law stuff that we were talking about a couple of weeks ago. And that's also important in the solar system. So for example, on Io, one of the moons of Jupiter, people are really interested to know how hot the lavas are, which are being erupted on that planet, because people have suggested the lavas are very hot. If the lavas hot, that means there must be massive melting in the interior of that planetary body. And if we can confirm that, that tells us something very fundamental, not only about melting processes on that planet, but it gives us some insight into how the early Earth would have looked when it was very, very hot and its interior was much hotter and much more molten than it is today. So some of this is going to be revision. So we've seen this a lot, right? So this is the reflectance remote sensing process. The emission remote sensing process is basically the same, because the design of the spacecraft will be different, but ultimately we're measuring photons, and the detector kind of doesn't know whether they're reflected or emitted, right? So it's basically the same. All we do is turn the sun off, and the surface itself becomes the source of the light. So again, this is passive remote sensing, right? Remember we spoke about passive and active remote sensing. Active would be the backscatter stuff when you shine light. Passive is the spacecraft doesn't generate its own signal, it just uses a signal that was generated somehow else. So in this example, the logic is the same. So here is a lava flow at Mount Etna in Sicily. It's kind of hot, and we might want to know the temperature of this lava, because lavas, when they're erupted, they're very hot, and they tend to be kind of runny. And while they're running, they can flow downhill under the force of gravity for great distances rather quickly. Right? As soon as it's erupted, the stuff that you see here is probably at about 1100 degrees C. Right? When lava is freshly born, its temperature is about the same as the eruption temperature of the lava, which might be 1100. At kiloaries, the eruption temperature is typically no higher than about 1150 degrees C. Right? But as soon as it's exposed to the atmosphere, it starts to cool. Right? The lava starts to lose heat. It loses heat by radiation furiously initially, and also convection, free convection and forced convection, so the wind blowing over the lava, which brings energy. And it also cools via conduction through the base. So as the lava loses heat, once it gets exposed to the atmosphere and the environment, then its temperature starts to fall as its internal energy falls. And as its temperature falls, it stops glowing, right? So this is fresh lava that's glowing because it's real hot. As it cools, its temperature falls down and then it stops glowing, right? This is still real hot though. This is like 900 degrees C, 800 degrees C. It's only not glowing because this is daytime. At night, this whole thing will be glowing. Right? So as it moves down a hill, it loses heat to its environment. It loses internal energy. As it loses internal energy, it gets increasingly sticky. So for the engineers, you would use a term like rheology, you would use terms like viscosity and yield strength. Okay? It just gets increasingly sticky as it cools. And as it cools and gets more sticky, eventually you reach a point where it can no longer fall downhill under the force of gravity, right? And in that case, the lava flow would stop. So that's a large part of lava flow modeling. You know, when they were doing modeling on the Big Island 5 years ago during the large eruption over there, a lot of it was concerned with what's the rate at which the lava comes out of the ground, and then using models to predict at what distance from the vent do we think the lava will become too sticky to flow any further. Right? So that might be the left-hand side of the science traceability matrix. Right? That's what the physicist cares about. They care about the rheology of this lava. And we know that the temperature is related to rheology. So the spacecraft can't measure the viscosity of the lava, right? To measure the viscosity of the lava, you've got to put a thing in that looks a bit like a mixing paddle, and then see how hard you have to turn it in order to get it to turn, and that gives you some information about the stickiness of the lava. Right? But we can't measure that, right? That might be what we want, but that's not what we get. What we do is measure a related parameter, which is our measurable. Remember the science traceability matrix? Right, so the measurable is temperature, because we know how it's related to viscosity. Now, fortunately, temperature is related to emitted spectral radiance, right? And we'll go over that again. Something which is hot relates a lot to spectral radiates a lot of energy. Something which is cool radiates not so much energy, right? And I'll remind you, but you already know the relationship between emitted spectral radiance and temperature is Planck's law. Right? And I think in this slide I'll just show you how to rearrange it to solve for temperatures. So, we measure spectral radiance. Same thing again, we have some scanning system which samples it from each pixel on the ground. Right. We have a lens, optical system that collects the light. We pass it through a spectrograph to split it into its different frequencies. We let that light land on a detector. Now here's the difference, and I'll talk about this next week. The detector materials for detecting long-wave infrared low-energy photons are different than the detector materials we use for detecting high-energy visible wavelength photons, right? So that's the difference, and I'll talk about that next week. This is the same, right? Once we get to here, these are just photoelectrons, same as we had before, in the presence of a bias voltage and a reference resistor. The more spectral radiance, the more photons that land here and cause photons to jump from the valence to the conduction band. We can measure that as a change in voltage or current, depending on how we've got it configured. And the rest of it's all the same. We have an analog signal, we digitize it, we convert it to a digital number, and in the lab you get an image of a lava flow. And as we did in the lab a few weeks ago, you could go into each one of these pixels in ENVI with the cursor location value tool, and you could get the digital number for that pixel in all of the wave bands. You could convert it to spectral radiance using the kind of calibration coefficients that we looked at, and you could put spectral radiance into Planck's function to work out what the surface temperature of the lava flow was. Okay. So thermal remote sensing, not a whole lot different. I've shown you this before. Did I show you this? You've seen this, right? You've seen this loads of times. Yeah, just a worked example of this. The key thing about this that I wanted to just briefly talk about is how you generate a continuous spectrum. This is for hydrogen, and then there's a bunch of, these names are just people that discovered these different transitions, right, early spectroscopists. And this is just a worked example about how, what's the frequency of a photon produced by the N3 to N2 transition. So we add enough energy to get a photon to go from here to here, and then after a billionth of a second, it relaxes back down, and in the process of doing that, it generates a single photon, right? And based on Planck's relation here, which I've just rewritten here, the energy of a photon is Planck's constant multiplied by the frequency. We can just simply work out what the energy of that photon would be. And because we know the energy, we can convert it to frequencies. Because we know frequency, we can convert it to wavelength. And we would say that a photon falling from level 3 to level 2 would generate a photon which had this frequency or this wavelength, which is the visible red part of the spectrum, right? Mm-hmm. So that transition generates one photon of visible red light, so we would see red, right? This isn't much good for remote sensing, right? I mean, people use this for information, but we like a continuous spectrum, right? Because then we can shine light of all frequencies on a target and work out which of them we lose to absorption, which can get reflected back to us, right? So how do we go from a line spectrum to a continuous spectrum, right? Do you remember this stuff, or ever heard about it? This is for an isolated atom, right? This is for a hydrogen atom, right? If we have a hydrogen atom and a hydrogen atom, they will both look like that, right? The distance between these different orbitals will be the same, and it will have these numbers. So you shine light on hydrogen here, if you shine the same light on it, you'll get the same photon emitted, right? But if we bring them together, we form molecular hydrogen, right? The exclusion principle says that we have to change one of those quantum numbers, right? Remember the exclusion principle? Pauli's exclusion principle. Basically, you can't have two electrons occupying the same orbital in the same state, right? So what that means is we take two hydrogens and make a molecular hydrogen. These electrons have to kind of adjust to each other, right? Because they cannot occupy the same state, because that would violate the exclusion principle. So the electrons have to adjust ever so slightly to form a bond, and that's chemical bonding, right? When you take two things and you stick them together, the electron clouds mingle and bond, and in mingling, those electrons occupy different orbitals than they did in their isolated state. That's a chemical bond, right? In doing so, all of a sudden, these electrons have occupied slightly different distances from the nucleus, so they will absorb and emit photons at an increasingly broad range of frequencies than they did when they were isolated. Okay? Does that make sense? You don't have to work that out, but does that picture make sense? So these are the isolated hydrogen, helium, uranium. We have these discrete lines, and sometimes the lines look a little like bands because in something like uranium, we have many, many, many orbitals, and they get very, very close together. And it looks like electrons are continuously falling towards the nucleus and radiating continuous spectrum of energy. They're not, it's just that the orbitals are so close to each other. Right? So Google it, that's something called the correspondence principle, Niels Bohr back in the 1920s. Here's just a picture of what hydrogen on the bottom versus molecular hydrogen looks like on the top. So this is the effect that I was talking about. Hydrogen looks like this, discrete lines and not many of them. And there aren't many of them because hydrogen only has one electron. Right? But if I take two hydrogens with one electron, then in order to not violate the exclusion principle, those electrons have to orbit across a range of different orbitals, which produces a range of different distances from the nucleus at which that electron can be found, the probability of it being found there. Right? And lots of different locations or orbitals with respect to the nucleus means lots of different wavelengths of light can be emitted. Because remember, if it's in a particular orbital and it absorbs a photon, it jumps up, in relaxing down, it radiates a photon of basically the same wavelength. So this is just hydrogen versus molecular hydrogen. Why does the sun emit a continuous spectrum? Well, it's a plasma. Why does the Earth emit a continuous spectrum? Because the Earth is the ultimate extension of what we're showing here, right? We've taken isolated ions, we put them together in molecules, and then we've taken molecules and we bang them all together into a solid, right? So in that case, you've got so much overlapping of electron orbitals that the electron orbitals are so numerous and they're so closely spaced together that it appears those things are absorbing and emitting over a continuous band of energy, right? It's basically like taking this, it's basically like taking this and putting tons and tons and tons of extra orbitals in here such that the target can absorb photons over a continuous frequency range, and in doing so it can also emit photons over a continuous frequency range. Right? And that's why solid bodies emit continuous spectra. The sun does because it's not solid, it's a plasma, so you've got lots of recombination effects. It's so hot that you're stripping electrons from nuclei, and then when they recombine, they cascade down the rungs of this energy ladder, emitting photons as they go. So plasmas are a little bit different, but so that's how we go from a line to a band to a continuous spectrum. So I just spoke about that because continuous spectra are useful, right? Spectroscopy is like line spectra, but as remote sensing people, we like a continuous spectrum. As I said, then we can shine it on a surface and we can see which wavelengths are absorbed. In thermal emission, because planets emit continuous spectrum, solid bodies emit a continuous spectrum, we can use that information for a few things. One, we can work out the temperature, but importantly, we can look at the wavelengths at which light is not emitted. We'll talk about that in a little while, because those are the wavelengths that encode the chemical composition information. So just bear that in mind, and we'll talk about it more again. And then this is just a picture that shows this. As we move atoms together, the energy orbitals increase, they split, and they split, they split, and then eventually it appears that you have so many that you have a continuous range of energy levels over which electrons can rise and fall, absorb light, emit light. And we go from line to band to a continuous spectrum of light. So I'm not going to talk about this much, you've seen this before. Right, so spectral radiance is the way that we talk about light in remote sensing, derived SI parameter, watts per meter squared per radian per micron, flux per unit projected area, per unit solid angle, per wavelength interval, leaving or falling on a reference surface, spectral extensors going out, spectral radiance, we divide by the Steradian term, and then we get this thing over here, and we spoke about this before. So, what can we do with this information? You've seen this before, okay? So again, Planck's blackbody radiation allows us to calculate the temperature of the surface without touching it. So this is the temperature sensing part of this. So if we want to know the temperature of lavas erupted on Io, we can just use Planck's law. If we want to use the temperature of cryovolcanism on Europa, we can use Planck's law to work out the temperature of those lavas. Again, all I've done here is plotted this one. Here, you can see the sun is up here, so 6,000 K. Did anybody miss this class when I was going through this? I mean, we did the spreadsheet, right? I gave you that spreadsheet, which is just includes this in a few columns in Excel, right? So you can produce these curves on your own now using that spreadsheet. Again, this is the thing that we measure, or this is related to it, right? Remember, we have to divide this by pi to get to spectral radiance. Yeah? But that is related to a whole bunch of constants. Wavelength, which we can just iterate through, and the only unknown is temperature. Right? So if we have a measurement of this, and we know the wavelength at which we made that measurement, we can easily invert this to work out the temperature of the surface. Right? So it's pretty easy. Right? So that's those oven thermometer things that people use. They don't work like that. We'll talk about how those detectors work next week. But that's the principle for thermal remote sensing. So there are a couple of shortcuts that you could potentially use to work out the temperature of a body. So are people familiar with Wien's displacement law? Right. So Wien's displacement law and the Stefan law are both derived from Planck's law. Right. So we obtain Wien's law by finding the turning point of that function, the maxima. Right. And if we do that, we find that the wavelength of maximum emission in microns is B, a constant, divided by temperature in Kelvin. So what this means is if you have a measurement that gives you a complete spectrum, then all you have to do is pick out the maximum value, stick it in Wien's law, and you can work out the temperature. Right? So for example here, take the wavelength of maximum emission here for the sun, 6,000 Kelvin, we drop a line down, we get about 0.5 microns as the peak. If we put 0.5 microns in that equation over there, then we would get 6,000 K. Right. For the Earth, the opposite, we go to 300 K, which is this one here. We drop a line down, we find that the wavelength of maximum emission is at about 10 microns. And then if we plug that in there, we get the 300 Kelvin, right, because it's much lower. So we get Wien's law by, it's the derivative of the Planck function. We can't usually use this to work out the temperature of objects using remote sensing measurements because we don't have a continuous spectrum, right? Remember, we usually have kind of multispectral measurements where we have 6 measurements, right? This is imagining, I can do this, but what if I don't have a measurement here, right? If I design a spacecraft that doesn't give me a measurement here, then I couldn't use this method to work out the temperature of the sun because I wouldn't know what the wavelength of maximum emission is because I never measured it. Right? Similarly, Stefan's law offers us a route to working out the temperature of a surface without touching it. So Stefan's law is the integral, just the area under the curve. Right? So here, this is the Boltzmann law, sigma t to the 4th, sigma is a constant, temperature. For the sun, it's the constant multiplied by 6,000 raised to the power 4, which is this. For the Earth, we're raising 300 to the 4 rather than 6,000 to the 4, so it's a much smaller number. But the point is, the area under the curve is different for a 6,000 K emitter than it is for a 300 K emitter, and is different from a 300 from a 350 K emitter. So if we knew this area, we could just invert it to work out the temperature. But again, we don't know the area under the curve. Right? We might be able to reconstruct it somehow, but we don't know it. It's not our measurement. Our measurement might be a measurement here, 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 and here. Right? So we really can't do those. Sometimes you see these as in elementary physics books as ways that you can work out the temperature or something without touching it. But really, we don't make the measurements required to exploit the Boltzmann relation and Wien's law. Right? What we do is make measurements at just 1 or 2 wavelengths. Right? So we can't use them. What we usually work out is something called a brightness temperature. Right. So the temperature is something that I care about, is its temperature, right? So if I wanted to work out the temperature of this table, the best way of doing it would be to use some kind of physical temperature sensor. right? If I really want to know your temperature, the best way of doing it would be to stick a mercury thermometer in your mouth for a little while, right? Now they don't do that anymore, right? They open your mouth and they shoot one of those things in, like the same thing that you use in the oven, right? That's a brightness temperature. They're not measuring the kinetic temperature of you. They're measuring a brightness temperature of you. The kinetic temperature is the temperature that's proportional to the translational kinetic energy of the molecules that are vibrating in this table right now. And the hotter it is, the more they vibrate. Okay? So that's really what I want to know. But the dentist doesn't stick a thermometer in your mouth, or the doctor doesn't stick a thermometer in your mouth, because it's inconvenient. What they do is point that thing in and they get a measurement. What they're doing is making a brightness temperature measurement of the interior of your mouth. So how does that work? Well, it works just the same. We're exploiting Planck's flat body radiation law, right? And what we're going to say is, I can't remember how I did this, so that's 10, 9, 8, 7, 6. So here what we're saying is if I make a measurement of spectral radiant excitance from a 300K radiator at 6 microns, I will find that I get a value of about 10.5 watts per meter squared per steradian per micron. So again, the way it works is, I don't know that, what I know is this. I know that I measured 10.5 watts per meter squared per micron, right? I also know the wavelength that I measured it at, right? Because I know the specifications of the detector and the camera. So based on that, I can just plug that radiance into this inverted version of Planck's function. So this is just that rewritten to solve for temperature. Okay. So I know the wavelength, which is 6. I know n lambda because I made that measurement, and by doing that, I will get a value of 300 Kelvin. Right? And if you look at this, it doesn't matter where I make the measurement. Right? So if I made the measurement at, let's try and take the same. If I made the measurement at about 18 microns, right? I would get a value of about 10.5. And as long as I plug 18 microns and 10.5 into that equation, I'll get 300K, right? Same as this. If I measure it at 10, I get a value of about 30. As long as I plug 10 microns and 30 watts per meter squared per micron in there, I'll still get 300, right? So it doesn't matter. But that's what we're making measurements of. We make measurements of brightness temperature, not kinetic temperature. But kinetic temperature is the thing which a scientist might really want to know, right? But again, it's this difference between the physical parameter and the measurable, right? So for a lava flow, the thing they might want to know is lava viscosity. The thing that's related to is temperature. The thing we're going to measure is spectral radiance to work out temperature from which they can work out lava viscosity.
This brightness temperature could be quite different from the kinetic temperature.
Yes, it could. So we're going to go through that.
Okay.
But yeah, that's the problem,
Huge
right?
number different.
If it was as easy as this, then it'd be great, right? But it isn't quite as easy as this. Although in some instances it's harder, in some circumstances it's easier. So we'll talk about that in a little while. But let's just start this performance modeling thing again, right? So we're just going to go through a few quick slides, and you've done this already, and you could use the spreadsheet that I've given you to just replicate all of these slides, right? So we're going to say, oh, I'm interested in designing an instrument to measure thermal emission from the Earth's surface. How much light do I have available, right? Remember, this was the first series of toolbox equations that went into that performance modeling exercise. How much light do I have available from the thing I care about, right? So on the Earth, I'm going to say, well, the Earth's average surface temperature is about 300 Kelvin, right? In your science traceability matrix, if I'm doing remote sensing of the cryosphere, ice caps and glaciers, that's too high, right? I would have to use a lower value because they're way colder, right? If I was interested in measuring lava flows, that's too low, right? Because lava flows are hotter. But just generically, I'm interested in the Earth 300K. I put that in Planck's law, solve for spectral radiance, and I get a curve that looks like that, right? Which tells me if I'm going to design an instrument to make measurements of the thermal emission from the Earth's surface, then there's no point designing an instrument which makes measurements of photons at 3 microns, right? Because the Earth is not hot enough to radiate energy at 3 microns. Ideally, I'd make my best signal to noise is going to be at 10 microns, right? Because that's the wavelength at which most of the energy is emitted from a radiator at 300 Kelvin. Okay. So if we imagine, again, remember, sunlight isn't shining on the Earth itself is the source. So when we were doing reflectance remote sensing, the first step was how much energy comes from the sun, how much makes it to the top of the Earth's atmosphere, how much makes it down to the surface. Here, that's where we start, at the surface. Right? So, it gets back to the point that you just raised about the radiation temperature, brightness temperature being different than the kinetic temperature. Is this the amount of energy which arrives at the satellite? This is the amount of energy that leaves a patch of dirt on the Earth's surface.
So no.
No, right. What happens to the energy?
Well, it has to go through the atmosphere.
All right, so that's one step. So we're going to lose some energy.
Yeah.
That's also in the thermal, we can also gain energy because the atmosphere is warm and it radiates up and down, right? It radiates down, and that's the greenhouse effect. Right? But yeah, so we have to account for the atmosphere. There's another thing we have to account for, which is the thing which we're going to exploit later to work out the chemical composition of this target. Right? At the moment, all I told you is this is a patch of dirt at 300 Kelvin. The term we're going to introduce now is the term which will allow us to tell you whether that patch of dirt is made of silica sand, or calcite sand, or plagioclase feldspar, or any other kind of mineral, right? And the thing is called emissivity. Have people heard of emissivity? Right? But you know what reflectivity, right? You know that, and we've spoken to death about reflectivity. You know how important it is, right? Emissivity is in the thermal infrared what reflectivity is in visible and shortwave infrared. Right? So here's an emissivity spectrum of quartz. Right? If we look, it looks just like a spectral reflectance curve, right? People agree? I have wavelength on that axis. But no, I'm now in the long wave part of the spectrum, not the short wave part of the spectrum, right? From 7.5 to 13.5 microns. On this axis, I have another of these unitless parameters, so between 0 and 1, right? And then I have a squiggle, just like we have in the reflectance spectrum. So emissivity epsilon subscript lambda is just a common way of denoting it. What does this curve tell us? We'll talk about this in a little while. People kind of know what a black body is. Yeah, kind of know what black body is, right? Now, at this point, we'll just say it's a perfect radiator, right? So we'll define it a little bit later on, but a black body radiates light, energy, radiation, at the maximum rate anything could do at that temperature, right? So nothing can radiate more light than a black body at a given temperature. What emissivity is telling us is, if a surface we look at has an emissivity of 1, that means it's a perfect emitter, or a black body. So black bodies, the emissivity spectrum of a black body would be a horizontal line at 1, and it wouldn't fall below 1. Okay? Because it's a perfect emitter. You know, if you express this instead of 0 to 1, 0 to 100%, and if you just read emissivity as the capability to emit light, then a black body would have 100% of all wavelengths, because it's the perfect radiator. If we look at quartz, we can say a few things. We can say that at 12.5 microns, quartz exhibits near black body behavior, right? At 12.5 microns, quartz emits 90% of the light it could do, even if it were a black body. So it's 90% efficient related to the black body standard. We can also say that at 9 microns, quartz only radiates, its capability to radiate is only 20% of a black body at the same temperature. Right? So in these curves, high values of emissivity indicate that that material is very, very good at emitting energy at that wavelength. And the closer it is to 1, the closer it is to black body performance in terms of its capability to emit light. Where we have a trough, the material is not very capable at emitting light, and its behavior is far from a black body. I'm going to show you some later, but you remember when we looked through some reflectance curves in ENVI and we saw that every single thing on Earth had its own unique curve with peaks and troughs in it, and the troughs corresponded to those wavelengths at which that material diagnostically absorbed photons, right? Beer's law and all that sort of stuff. Right? The same is true for these curves. So every single thing on the Earth has a unique emission spectrum, right? Because of its chemical composition. The wavelengths at which the troughs occur are the wavelengths at which the absorption coefficient is high. Remember Beer's law, it was absorption coefficient was the thing that was driving the peaks and the troughs. Everything on Earth has a unique emission spectrum. The troughs correspond to wavelengths at which a material characteristically absorbs light. Because it absorbs light at that wavelength, it can't radiate light at that wavelength as efficiently as at other wavelengths, and that's why it's a trough. So another way of saying it in this part of the spectrum is that these wavelengths, the chemical composition of quartz causes emission to be impeded. Right? Write that down, because it's a common sense and not too far from the truth explanation for why these curves have the shape they are. The troughs are wavelengths at which radiation is impeded. And these have special names. This is called the Rastrallen band. So you may have heard of that, Rastrallen band, and the German residual rays, because they used to use this phenomenon for filtering. And then the shoulder here is called the Christiansen frequency. I don't know if you've heard of that. But you don't have to remember that. Just remember, troughs, emission is impeded because the stuff quartz is made of absorbs light at those wavelengths. So the amount of light radiated by that 300K emitter isn't this, right? Because that's assuming the 300K patch of dirt is a black body, right? In reality, it's not a black body because black bodies don't exist. In reality, it is less efficient at radiating light than a black body, which means it radiates less light than a black body. So I have to account for the emissivity to work out what the actual surface leaving radiance was. Remember we spoke about surface leaving reflectance. Here we're going to talk about surface leaving radiance or surface leaving emission, right? So I have to work out how crappy my real world target is at emitting energy. And I do that by taking account for its emissivity. So again, like I did with the reflectance thing, just to keep these curves a little bit similar, for this modeling, I'm just going to assume that the emissivity of this target is 0.9, right? So a flat 0.9. Okay. So by accounting for the emissivity, the grey curve becomes the red curve. People see how I did that? I just took every single value on the grey curve and I multiplied it by 0.9. And that gave me the red curve. So in your spreadsheet, I gave you the spreadsheet last week about the performance modeling where we had a spectral reflectance column. Here we would just have a column which is the emissivity. So if you wanted to do it for a real target, instead of using 0.9, you just use that curve in a column in your Excel spreadsheet. Right. Okay? So this is the energy that could be radiated from something at 300K if it were a black body, but it's not a black body. It's a real thing with a real emissivity. I'm just going to assume the emissivity is 0.9. It could be anything. And I'm going to multiply every point on the grey curve by 0.9, and that gives me the red curve. Right? So this is the surface leaving radiance from something that has a temperature of 300 Kelvin. Again, in this part of the spectrum. It has to pass through the atmosphere, right? But it only has to pass through the atmosphere once. So, what I'm going to do there is, and I showed you this last week, remember those curves of atmospheric transmission? That's another column in the Excel spreadsheet. I just take every value on this grey curve, the lower grey curve, and I multiply it by my atmospheric transmission. And that gives me the red curve, which is the top of the atmosphere or at satellite radiance from a target at 300 Kelvin with an emissivity of 0.9. So this would be the first point in your performance modeling. Right? So if you were going to study the surface of Pluto, you wouldn't use 300 Kelvin. You'd work out what the surface temperature of Pluto is, and you'd plug that in. Right? And you'd ask somebody, okay, and I'll show you how to do this next week. I've worked out what the equilibrium temperature of the surface of Pluto should be. Right? It's relatively simple. But I've got that temperature, but I know Pluto is not a black body, right? So you go to a geologist and say, well, what's it made of? What's the surface of Pluto made of? And they give you a name, some ice, right? And then you go away to a spectral library and you'd find the emissivity spectrum of that ice, right? And then you plug it in here. And you go from that curve to that curve. And then you ask them, well, does Pluto have an atmosphere? And they say no. And you say, well, okay, then I'm done. Pluto's kind of cold, this is what it's made of. On the basis of that, you could just use this to predict how much energy should be received at the satellite from that target at that temperature. Okay? So this is simpler than the reflectance case, right? We're just doing fewer steps. But the math is all the same. And I've just shown this just to, this is an example we looked at in lab, but just to show the difference between the visible case and the thermal case, right? So we did this to death over the last several weeks, where this was top of the atmosphere light, this was the light that made it through the Earth's atmosphere, this is the light that got reflected from the Earth's surface, this was the light that managed to get back through the Earth's atmosphere on its second trip, and for the Landsat data we made measurements in these bands, or these wavelengths, right? And that allowed us to produce false color images that look like this. Okay. Where in this case we have 754 displayed in red, green, and blue. Landsat also has a thermal infrared channel, which makes measurements all the way out there at 12 microns, so the grey bar. Okay. It's just a single channel, so it just gives us single grayscale images where dark is kind of cold, so this is a cloud, and lava is kind of hot. Right? So dark is cold and bright is hot. And you can see just down here. Right? For planetary type remote sensing, this is really biased towards the Earth, right? So you'll notice here, I can't make measurements of thermal emission. It's very hard to make them at less than about 8 microns, right? The red line is how much energy makes it back to the satellite. Not much energy makes it back at 9 microns or 8 microns, right? And hardly any energy gets back above 10 microns, right? And this is because of Earth's atmosphere. There's a huge carbon dioxide absorption feature out here, right? These lava flows are radiating a ton of energy here, but Earth's atmosphere absorbs it all. If you're looking at a planetary body that doesn't have an atmosphere, then you're freed from that constraint, right? If there's a particular emission spectrum feature which is diagnostic of a material you care about mapping at 20 microns, if that material exists on Earth's surface, there's nothing you can do about it because Earth's atmosphere doesn't allow you to make measurements of that wavelength. But if that material exists on an asteroid or a comet or a planet without an atmosphere, you could design a sensor to make that measurement, right? And you just go through all the steps that we've just gone through. So I'll give you just a worked example and just throw these things in and show you exactly where you put the different terms when you're multiplying stuff out. But pretty easy to work out the temperature of a target, right? We need to know the emissivity and the transmission of the atmosphere. We can also just look at thermal images to work out something about the physical structure of materials on different planets. So the simplest way we can do it, this is a thermal image of the Earth. This teardrop-shaped thing is the island of Montserrat in the Lesser Antilles in the Caribbean. Have people ever heard of that? Tiny little island. The pixels here, the spatial resolution is about 1 kilometer. Tiny little island, and in summer of 1995, a volcano started erupting, which basically, this island used to have 12,000 people living on it. Now it has about 4,000 people because it just totally wrecked the lower 2/3 of the island. The bright pixels here are hot, right? So we look at this image and clouds are cold. The ocean is slightly warmer than the land because this is a nighttime image. But the lava is really hot, right? This is the lava dome at the summit of the volcano. So you can just use these images to say that's hot, that's not hot. Right? Another way you can use it is work out things about the rate at which different targets heat up and cool down during the day and the night, which tells you mainly something about their density. Right? So if we look at these two images here, this is an island called Réunion, which is in the Indian Ocean. That's a volcano called Piton or Fournaise. So these were acquired at different times, right? On the right-hand side, you can see a lava flow, which you can't see on the left. But if we just ignore the lava flow, one of those was acquired during the day, and one of those images was acquired at night. What do you think? Which is the nighttime image and which is the daytime image?
It's the one on the right nighttime because the water's warmer.
It is. That's right, yeah. So there are a couple of other things that tell you that it's night on the right and day on the left. And one is the impression of topography. Right, so if you look, the one on the right looks flat. Right, the one on the left looks like a kind of mountainous, rugged island, a bit like Hawaii. The one on the right, you can see the features as the one on the left, but there's no impression that it's rugged. Right, it's very flat. And that's because the one on the left includes the effect of solar heating. So again, these are just temperature maps. Right? Bright is warm, dark is cold. On the left, the sun has been shining on the slopes which are white. Right? The sun is shining from this kind of direction. This has been heated up. This is not in direct sunlight, right? So it's shining from here. This is in shadow, so it's cold. This is facing the sun. This is a slope facing the sun, so it heats up and it gets warm. But we don't get that at night time. So that's one of the simplest cues you can use to work out differences in day versus night. Which way have I put this together? Well, that one might have been out of order. Anyway, we'll come back to it. But just to show you how to work out the temperature of surfaces within these pixels, right? So let's flip back to temperature. We have our spectral radiance leading the surface, which we want to know, right? Because we can plug that into Planck's law and get the temperature of the lava within these pixels. Right, and let's say its kinetic temperature is 1300 Kelvin. Right. That energy, not all of it leaves the surface because lava is not a perfect radiator, it's not a black body, so lava has an emissivity and we have to account for it. That energy passes up through the Earth's atmosphere, which has a transmissivity which is less than 1, so we have to account for it. And at the satellite here, what we end up with is a thing called at-satellite spectral radiance. And I showed you that we have typically have these calibration relationships where L lambda equals gain times a dn plus a bias, equation of a straight line type thing. Right. In order to work out that kinetic temperature, we have to kind of rearrange Planck's law to just look something like this. Right. So this is Planck's law rearranged to solve for temperature. Right. And in here, you see I've got L lambda corrected. And L lambda corrected is the thing that I just calibrated out of the data divided by the transmissivity multiplied by the emissivity. Right. So if I don't do this, if I don't do that, I'm going to work out a brightness temperature. Yeah. If I include that, then I will be attempting to correct my brightness temperature to derive a kinetic temperature. Good? And obviously this is a correction, right? So the worse job I do on this, the less close my derived kinetic temperature will be to reality. So again, doing this on planets with atmospheres is harder, because the atmosphere is typically the weakest link in this chain. So that answers your question about the brightness temperatures and the kinetic temperature, right? The difference between the two is how well I know the transmissivity of the atmosphere and how well I know the emissivity of the surface. And here's just an example. This is from a mission that NASA sent to the Jupiter system back in the early 90s, late 80s, early 90s. So this was a thing called, these are data that were acquired by the Galileo NIMS sensor. So it was a near infrared mapping spectrometer. These are, a couple of years ago, people saw the curtain, actually quite recently, they had the kind of fire fountain in on the Big Island, right? Remember that just a couple of months ago? This was fire fountaining at a volcano called Vashtar on Io. So Io is the most volcanically active body in the solar system. All of these little black dots that you see are volcanoes on the surface of Io. Io is active because it's close to Jupiter, and Jupiter is causing Io to stretch as it goes around in the orbit. And as you stretch it, stuff that's interior, you get frictional heating as it rubs past each other. And that causes interior melting of Io on a large scale, which is why you've got all these volcanoes. NASA wants to go back to Io and make measurements of these kind of things, right? That's one of the things that's going to be funded the next time NASA's New Horizons competition is competed. Somebody's going to get, well, it's one of 5 things. In a few years' time, when they recompete, somebody might get $1.5–2 billion to go back to Io and make the kind of measurements that we've just discussed. How hot are the lavas that are erupted on the surface? So if we go back to this thing about working out whether something is dense or not dense based on day-night temperature pairs. So the reason I showed you those day-night temperature pairs is because they can be very useful. Looking at the amount of energy radiated by something during the day and the night tells us a lot about how it's made up. Right? And we encode that information in a thing called thermal inertia. So this takes a little bit of getting it right, and it's a bit like chewing gum while you're doing something with your left hand or your right hand. You have to think about how you say it. So let's imagine that we have sunlight shining on the surface of a planet. Okay, and we're going to call that solar insolation, and it's this plot over here on the left. So this is local noon, when the sun is highest in the sky, so we have most sunlight striking the surface of the planet. And then this is midnight, right? The sun's gone in, and the planetary, the amount of sunlight striking the surface has fallen down to the minimum. As we shine these photons on the surface of a planet, then they will be absorbed. Right? And typically, the darker something is, the more sunlight it absorbs. Right? And as it absorbs the energy, then it will heat up. Right? And its temperature will increase. So during the diurnal cycle of solar heating, if we look at a surface on a planet, we will find that its temperature, and there'll be a little bit of a lag, but its temperature will increase and then fall. Right? While the sun's up and it gets higher and higher in the sky, and that cosine theta term, right, is getting higher and higher, the amount of the input of solar energy in terms of joules, right, the joules of solar energy which are striking the surface will go up. The target will absorb that energy, and its own internal temperature will increase, and it will get hotter. And then as the sun goes from local noon and it starts falling, the cosine theta term starts to dominate again, and less energy will strike the surface. And the surface will radiate that energy, and therefore its temperature will fall. And then when the sun goes down, the surface is no longer receiving energy, and it just radiates energy into space until eventually it reaches a minimum temperature, which is the middle of the night, and then the whole cycle goes again. Right? I've just drawn these 2 things here because these encapsulate this thing called thermal inertia. So materials with a low thermal inertia tend to have a higher amplitude in this diurnal temperature cycle than materials with a higher thermal inertia. So inertia is a resistance to change. Right. So if something has a low thermal inertia, that means it has a low resistance to change, therefore it changes more. Okay? And you agree the red curve changes more. The delta T is larger. It gets hotter and it gets colder. The material with a high thermal inertia, that's dampened, right? It doesn't get quite as hot, it doesn't get quite as cold, right? Because it resists the change. The main thing that's driving this is the density of these rocks. And I'll show you a picture on the next slide about how that works. But I've just plotted some numbers up here where we have thermal inertia on the y-axis, and then we have the density of a bunch of different materials here. And do people agree that there's a decent positive correlation there between thermal inertia and density? Peridotite is what the Earth's mantle is made of. It's a very, very dense rock. Pumice, some people still use that to exfoliate themselves in the bath. I don't know, I haven't seen that for a while. But it's a very low density rock, right? Pumice floats on water. The reason for this, we're going to dive back into one of these things. You remember in the when we were talking about Beer's law and we had grains of sand on a beach and we were kind of tracking photons through grains of sand? One of the main reasons people have used this in planetary science is to work out whether surfaces are solid rock or whether they're ground up, smashed up rock in the form of soils and powders. So if I take a solid rock, its density will be higher or lower than the same rock ground up into a powder. The units of density are kilograms per cubic meter mass per volume. So if I take a solid chunk of rock and then I ground it, the same thing up into a powder, will its density increase or decrease? Going from solid to powder. Going from that to that.
It decreases.
It'll decrease, right? Because all of a sudden I've got all these air voids in there, and the air has got mass. So in terms of mass per volume, that is much denser than that, even though the material hasn't changed. So we would expect this, on the basis of that, I said materials with a low thermal inertia, we'd expect a more rapid swing in temperature. And with a high thermal inertia, we'd expect a more subtle swing in temperature. So on the basis of that, do we expect this to have a higher or lower thermal inertia than this?
Wait, low inertia is high resistance.
So this is the way that, this is
My
why it
mind
plays
was
tricks with
slow.
your mind, right?
Okay, wait. I think I have
So
mine.
somebody remember this. Somebody remember this. Materials with low thermal inertia,
Uh-huh.
right, tend to be less dense, right?
Okay.
Shale, scoria. Materials with high thermal inertia, so the low thermal inertia stuff is the granular stuff.
Mhm.
The high thermal inertia stuff is the solid rock.
Okay.
And the reason for that is, so I'm going to have the same sun, I'm going to have the same rock, and I'm going to have a solid rock with no air voids. Right? And remember, on a planet, there's no air in here. It's just something that doesn't conduct, right? But it lowers the density. So solid rock, grind the same stuff up into some kind of granular powder. I'm going to shine the same number of joules of sunlight onto both of these surfaces, right? Which means the amount of energy arriving at the surface is the same for both of these things. In this case, the atoms at the surface will absorb some energy and they'll start to vibrate, right? Their internal translational kinetic energy will increase, right? Because they're getting hotter, kinetic theory of matter and all that stuff. And they will jiggle against atoms that are just next to them, right? And those atoms will jiggle and they will pass that on to the next layer and the next layer and the next layer. And this is what we call conduction, right? Heat transfer by conduction. So jiggling atoms here will jiggle atoms next to them and so forth and so forth. And that energy from the surface will be conducted or it will dissipate into the body of rock. The same thing will happen here, right? This surface receives the same amount of energy and the atoms here will jiggle in the same way that these do, right? But conduction only takes place via matter-matter interactions, right? Solid-solid interactions. You have to jiggle the next row of atoms. Right? Conduction doesn't take place across a void. Right? We don't get conduction across air, right? Or a void. It only happens when sand jiggles against sand. Right? So what that means is heat transfer by conduction from the surface down is much less efficient for the granular material than it is from the solid material. Right? People see that conduction is not impeded here because I've got solid on solid and I can just pass that wave down. Whereas here I have these voids which are basically resistant to conduction. Right? So conduction isn't as effective in the granular material as it is in the solid material. So if I'm shining sunlight on this pile of granular material, right, and it's accumulating at the surface, but it isn't being conducted very effectively, then I'd expect this surface to heat up, right, quite effectively, because all of these photons, all of these joules of energy are just going to accumulate near the surface, because this stack of stuff isn't very good at shipping it to depth. Whereas on the other side, I would expect the surface to heat up less, right? Because it is efficient at getting rid of the excess energy from the surface down. So that is this. Right?
Okay.
The low thermal inertia material, shale scoria. So scoria is, if you've been to the Big Island and you've been, it's like volcanic rock which has lots of air bubbles in it and gas bubbles in it. So it's not very dense. It's not like lava. It's not very dense. So low thermal inertia materials, which will be the material on the left, right? They heat up quite a lot during the day when you shine sunlight on them, because they're not very good at shipping that energy away from the surface. And with the satellite measurement, we just measure the surface temperature, right? Whereas the solid rock is the high thermal inertia material. It resists a change in its temperature, and it resists a change in its temperature because it's pretty good at shipping energy away from this interface. Okay, you shine all this energy on me, but I'm going to resist heating up because I'm going to pass it on. So people have found that in the planetary community, have found that useful. Many papers have been published to produce rocks, maps that look like this. So that's a map of the surface of Mars, where they've quantified thermal inertia, right? Whereas red is high thermal inertia and blue is relatively low thermal inertia, right? The blue areas are low thermal inertia. Remember, low thermal inertia meant that it wasn't resistant to change, right? It had big temperature swings. And we said that it was granular type materials which tended to have low thermal inertia, right? The big blue areas you see there on Mars, these are the kind of lowland basins. So those are the areas that NASA has traditionally sent rovers to, because they figure the lowland basins are maybe former oceans, or at least areas which received a lot of runoff and sediments from highland areas on Mars. And they like those areas because the most recent Mars rover, they put it on an outwash channel because they figured it was in one of these low-lying areas, and they figured at the past when Mars was warm and wet, water flowed, and water from many tributaries came into one big river and then dumped it out into a lowland area. So they like going to those kind of areas for a couple of reasons. One, they figure it's a good mixing site, right? So if there's life over a large area, the best place to look for it, if you can only look in one place, is probably a place where lots of material was sourced and dumped in one location, right? So if you want to study the chemical composition of the North American continent, going and collecting sediment from the Mississippi Delta is a good place to start, because that river carries sediment from all over the United States, right? People see that logic? Okay. So that's part of the reason NASA has studied these lowland areas quite extensively. All of the rovers have been dumped in one of those blue areas that you see. The other reason is when they were doing the aerobraking thing, when now they're using these kind of sky cranes and stuff like that because the rovers have got so big. But 30 years ago when Sojourner went to Mars, they put it in one of those big inflatable balls, right? And they dropped it, and it hit the surface, and it bounced around, and then it dumped the rover out. The lowland areas are pretty good because you get more of an atmospheric braking effect on Mars because they're lower, right? So when you go to Mars, Mars doesn't have a massively dense atmosphere. It's about 100 times less dense than the Earth's atmosphere. But there is some atmospheric drag. So you can use that to decelerate any descent probe that you send to the Martian surface. And the lower the surface, the more atmospheric drag you can benefit from when you're decelerating a probe, right? In terms of mission design, that's a common criticism is the scientists want to land on the highland areas, which are higher, but the engineers don't want to go there because it's a much greater engineering challenge to decelerate and not crash. Use NASA's discredited lithobraking technique. But they're getting away from that now, so the big rovers that they've just sent, they're too big to put in a big ball and just crash into the surface and hope they survive. So where they're now using those kind of helicopters and gimbals to try and slowly lower the rover onto the platform, onto the surface of the planet, rather than just letting it crash and spill out. So I've been through this before. You know, we've spoken about that. Why don't we have a break for 10 minutes until 12, and then we'll come back and finish off. Okay. We'll start with that.
So does the part of the moon that faces away from us most of the time have a lower thermal inertia? Because it's like hit with asteroids more often, so it would be like...
It isn't hit with asteroids more often.
No.
The difference between the near side and the far side, the near side, the near side has all the craters on it, which were like volcanism around 3.9 million years ago. So the near side has the Maria, which are basically basins that have been flooded with lava, a bit like the lava on the Big Island. But the asteroid strike rate is not any different.
Okay.
Just kind of look that there were some big hits on the near side which were flooded to form the Maria. But the moon's not a very good target, right?
Yeah, it's pretty small.
There's more crater patterning on the far side, though, but isn't that because of the way that it formed in the first place, not because it actually gets hit more?
No, if you look at the moon, were it not from the Maria, the near side would be just as cratered as the far side.
Right.
It's just that we had these, about 4 billion years ago, 3.9 billion years ago, we had these several large impacts that caused lava to be erupted into the basins. And then that flooded them with lava flows, right? So those are the Maria. But that happened at the end of what people call the late heavy bombardment. So prior to 3.9 million years ago, the moon was 4.2 to 3.9, the moon was just cratered all over. And then we had these impacts, they flooded with lava, but after they solidified, the impact to flux fell off rapidly, which meant those Maria weren't cratered anymore because there weren't any impacts to be had.
And on the far side, there was no lava filling to
Right.
disrupt those crater patterns.
Right. Yeah. There are some density differences as well, right? I mean, the moon is gravitationally stabilized. It shows us that face all the time. Have you heard about this gravity gradient stabilization of spacecraft? You heard about that? So, if this is a satellite, right, and it's going around a planet, make sure that's on, and it's going around a planet, right? Imagine I've got a camera here that I want to point at the surface of the planet. This works out as a pretty good passive technique for stabilizing that spacecraft so that this end looks down, right? Because that's the denser end. So I can tip it out of a spacecraft and it might be tumbling. This is not a very good thing actually because it's sloshing around. But imagine that's ice. It's tumbling around, but slowly gravity is going to cause that to point down.
Oh.
And at that point, it will just stay there. And it will do that around the planet. So gravity gradient stabilization is the cheapest way of making a satellite point in a particular direction. Right. Sorry, I've used your thing.
Okay.
And the moon, the near side of the moon points at the Earth because there's a mass imbalance between the near side and the far side of the moon, which causes the near side to constantly be gravitationally locked so that it doesn't point in the opposite direction.
Does that happens with most orbiting bodies, or not, like tidal locking just is generally the thing that most orbiting bodies will do eventually?
I don't know enough about it, but most do not, right? I mean, we're not tidally locked with the sun. We rotate.
It's because like the same tidal forces with like stretching, doesn't that kind of like oblong shape is what causes the mass difference?
So on the moon, it's not a tidal thing. So that's just like a physical, that is constant in the moon. So the interior of the moon is not molten to any great extent. there's just a density asymmetry which causes the near side to be gravitationally locked, so that it always points down towards the Earth. Bodies which are large enough or young enough to have retained enough of their initial heat from accretion, or have been endowed with enough radioactive elements to generate extra heat, can be molten or semi-molten in the middle, or at least kind of soft, right? In that case, three body effects. So if you have the moon, the sun, and the Earth, then the interaction of those effects can cause a planet to bulge and contract as it moves around in its orbit. So Io is an extreme case, right, with Jupiter. But it's not just Jupiter, it's the interaction of Jupiter and Jupiter's moons which cause it to flex, right?
Mhm.
The Earth also has those tides. On the Earth, mantle tides are about 1 meter, right? So the Earth expands and contracts because of the mutual interaction of the moon and the sun's gravity, and it flexes by about 1 meter out of
13,000?
6,700 is about the radius of the Earth, kilometers, right? So add another 3 zeros onto it. It's about 1 meter. It's about 1 part in a billion, in a 10 million. But it does give rise to some heat because as you flex it, these tidal forces
So
flex
that's
it, you
like
get
not
frictional
enough
heat.
of a mass imbalance to do what you were talking about stabilizing.
Well, it's not a mass imbalance because it changes constantly, so it's not something that's locked in, right?
I think I might go to the 8th floor. Still.
I know. I always go to the vending machines, and then I remember that there's like unlimited snacks up there.
No,
I'll put
no.
one resistor on, and then I won't feel bad about taking it.
I'll just like be in there for 5 minutes, just move a PCB around, you know?
Take a look inside the cabinet. Like, I deserve this.
Like take out the lead thing, look at the radar, you know, you really like have to look like you're doing
Scratch your
something.
head a little bit. You're like, all my hard work. Guess I need a protein bar.
Like look at something under a microscope. Then
Make
you-
sure someone sees you do it too.
Turn on the oscilloscope.
So I thought I could get this thermal camera working, but I'll have to do it next week when we're talking about thermal detectors. It seems
Old.
it is old, and I have that old computer which still has a FireWire port, but it seems like the FireWire is not working anymore because it wouldn't do it by the laptop, and for some reason this doesn't fit.
So cold.
It says that you're supposed to have an external device for it to be able to.
Well,
use
I think it's
components.
so. This is just like an old video cable, right? And it fits in there fine, but and there's a yellow hole at the back of this which says video, but the cable itself will not fit into the hole. It goes in partially, but then there's this thing which will not let it go. I'm not sure if I can find an old television.
Something like this.
It's this one, the review.
Yeah, okay, so for,
Mhm.
like I said, 4 pages, that's
18 minimum, so yeah.
Yeah,
3
so
to
that's
4
like-
a person.
1,000 words. That's a lot. That's why I said,
Whose computer is this? Is that yours?
you know, to put
Yeah.
everything together. So that's why I think you could just politely ask the Savannah to submit. Somebody has to put it together, and if hers is not,
Well, it only needs to be 18 pages and there's 6 of us. We can do 3
is there a
pages.
six yet? But still,
But still, I
you know, if everyone is working on do the same thing, then you're not going to cover everything. So you have to look at it and see which area is missing.
Yeah.
Okay, I don't think anyone wants to do software, so I think I'm safe. I'll
Mhm.
just go ahead and do that. But other people could just break
Yeah,
down
we'll
what
break it
Savannah has and
Yeah, we'll break down the rest of it.
So that it would be like it
Mhm.
as as the same material, but it needs to look like it as a.
Mhm.
So you're a
So
diet.
anyway, I was
On what?
A diet.
I'm not, but my roommates, my new housemates that I live with, buy the Costco packs. So then, like, I started drinking it
oh, you
in
should.
the afternoon, like when I didn't want to drink a coffee. I was a vitamin water girl, like the energy one, but
You don't like Coke Zero. I think
I
Coke
just-
Zero is okay.
I'm an original
Ah.
Coke person.
so is my brother. I think I like the diet taste better.
I don't like,
I
it's
don't
only
like diet
30%
anything,
of
so I
people
just
like
don't drink
taste aspartame or something, like 70%.
I can taste it, but I kind of
You
like
like
it
it?
better. Like, I never drank Coke ever. I was always like root beer, Dr. Pepper.
Yeah, I like that.
Oh,
I
there's another religion there. It's whether
Yeah.
you are a
Yeah.
Coke person or a Pepsi person.
My girlfriend's friend drinks like a 2 liter of Dr. Pepper and she's crazy.
That's crazy.
And she's
Yeah, I
like
never, my mom never let me drink soda growing up. Like, I could have like Sprite every once in a while.
I could have a Sprite like maybe once a year.
Yeah, like once in a blue moon we'd go out for dinner and she'd let me have a Sprite. So like this is like within the last 3 months.
With
It's
me and my girlfriend, we basically just can't get anything because I just didn't have the childhood drink.
That's how my brother is. Like I can kind of control it, but when my brother gets soda, he'll get like 4 refills
I
at a
don't,
restaurant.
I don't like do that, but because I drink a lot of seltzer, so that's kind of just
So
what
you
my
like the
replacement is.
bubbles?
I just like the bubbles.
I just drink a lot of coffee. Like this is instead of drinking.
Hot coffee. Or
Yeah, hot coffee. This is instead of my like 2 to 3 cups a day. Cause then I was drinking it like at like 3 p.m. and then I couldn't sleep.
What I always do is like if I have like a longer shift at work, it's like I purposely don't drink caffeine. Oh, I purposely don't drink caffeine too much throughout the week, and then if it's going really slow at work, I drink a monster that we have there.
See, and I had a phase when I was working in a restaurant last year. I had a phase where I was drinking the energy drinks and I was going to the gym a lot. But those are so much caffeine. I was like, I need to chill it on
Yeah.
those.
It makes me like not here, and it hurts my head, and it's like horrible for me. But at the same time, I just want to get work over with. So it's like
And I notice when I start working out consistently, I start drinking more caffeine.
You drink more?
I drink more.
That's interesting.
I know. Like, I haven't been working out, but when I do, like when I'm going to aerial a couple times a week or like hiking Cocoa Head, I like need caffeine afterwards. I crash after a workout.
Maybe it's true because if you do more exercise, for me, if I walk a lot, I sleep a lot
I
more.
sleep way
So
better.
that's why
Yeah.
you need more caffeine to
Like
keep.
in the moment, I have like the endorphins and the energy, but then I get home and I shower and I'm like, and I pass out.
I like it now that I had so much to do. When I go to bed, I will be sleeping.
Yeah, but I don't sleep well because now I've been dreaming about my math problems, and I have nightmares that
Is it
I
her
like
eyes or
have to solve
eyebrows
an
that are
integral
no
in
glasses.
front of everyone.
Oh, yeah,
And I
that
have
makes
like
sense.
nightmares that I can't solve math problems.
But
So
you're done with your calculus. There's not a lot of
Yeah,
integral,
but I'm
and
still
even
I'm
in
in my
calculus.
stats class, and it's a lot of
that's okay.
integrals in that.
Oh, but
and
then
like-
you learn it.
Yeah,
Is
and
the
then like
stats
I also
class help?
teach Math 140. Like I'm in LA for it, so I have dreams that I can't teach the topic to the students, and I have like
But 140
nightmares
is
of
okay.
solving
I've been
math
having the
problems.
problems.
Dude,
Yeah.
I have such bad dreams about like not being able to do my work, like not knowing how to do math
I have
problems.
like this consistent dream that it's me waking up. I'm driving my car, but I just keep crashing it
Oh
to
my
school.
God.
And then I get to school and there's a quiz, and I
Oh, I
gotta
have that all the
keep doing
time.
like 1,000 calculus problems, and I'm just like,
It's like me and just like a white room, but like a whiteboard, like an unlimited whiteboard, and I just have to sit there and do math my whole dream. It drives me crazy.
So have you been doing in class the model fitting stuff?
In
That's
which
in Duncan. No, Duncan's
my
class
stats
is in the
class?
in your stats class. So you do. The
Are you
model.
taking math 372?
Yeah, are you?
I took it like a year ago.
I'm in it right now.
Yeah, and that class is tough.
It's
one of the ones where it starts off like super easy with like the just probability trees, and then like it very
we're
quickly.
hitting statistics right now, and I can tell it's.
Once you do like Gaussian and
Yeah.
Bayesian stats, it starts.
Oh, but that's going to help you.
No, it's helped a lot. It's helped a lot.
I
Right.
mean, the statistics always does.
Should we get going? Okay. So as I said before, emissivity is useful for several reasons. First of all, if we're going to try and estimate a kinetic temperature from a brightness temperature, we need to know it, right? Because it's part of our correction. And secondly, this spectral emissivity term is the thing in the thermal infrared that encapsulates the chemical variation that we're interested in resolving to work out whether surfaces are different from each other and try and chemically fingerprint what they are on the basis of their spectral emissivity. We spoke about Planck's black body radiation law is great, but it only applies to black bodies, right? And then I asked you if you knew what a black body was. Lots of people have different definitions of a black body. This is a useful one. Again, we're only talking about this because Planck's black body radiation law is the one we're going to use, right? But if we imagine, people talk about a black body as being a perfect radiator and a perfect absorber, right? A black body absorbs and emits at the ideal rate, or nothing in nature can absorb and emit as efficiently as a black body, right? Another interpretation is black is black, therefore it absorbs everything that lands on it. Right? Another kind of half-assed definition of a black body that you occasionally use. There's a definition of perfect radiator is one that radiates the maximum number of photons in unit time from a unit area in a specified spectral interval into a hemisphere that anybody at thermodynamic equilibrium at the same temperature can radiate. So thermodynamic equilibrium means no change, right? Or no net change. It doesn't mean that nothing's happening, it's just that over time there is no net change, right? So if you think about what that means, if you imagine a brick there on the left-hand side, well, in the middle, right, we've got brick levitating in a room, and we have walls around the levitating brick. If the brick is hotter than the wall, then what will happen to the brick? It'll radiate heat, right? It'll cool. And it will radiate photons to the wall. And what will happen to the wall?
It will absorb.
It will absorb, and because it absorbs, what
It's
happens?
hotter.
It'll get hotter, right? Conversely, if the wall is hotter than the object, then the inverse will happen. The wall will radiate. Its temperature is higher than the brick will absorb energy, the brick will heat up. But eventually you'll reach a point when the temperature of the wall and the temperature of the objects are the same as each other, right? And at that point we say that they're in thermodynamic equilibrium with each other, right? That doesn't mean nothing's happening. The wall is still radiating photons and absorbing photons. The brick is still radiating photons and absorbing photons. It just means there's no net change, right? They're in thermodynamic equilibrium with each other. So that's the important part of the black body thing when you get in the weeds. So people occasionally say, well, why isn't my oven a black body radiator? And it's like, well, because you have heat loss via convection and conduction and all sorts of other stuff. Black bodies are only relevant to radiative heat transfer. Right? But it's not that important, but that's just an explanation of what thermodynamic equilibrium means. And we get to this point where the wall and the object are perfect radiators and emitters, because if they weren't, they wouldn't be in thermodynamic equilibrium, right? If one was less efficient than the other, then they wouldn't have the same temperature. Because one would not radiate as much as the other, or one would not absorb as much as the other. But just looking at how we compute this, so that's just something so that you've got that in your notes, right? But what does this really mean in terms of remote sensing? So, as I said, emissivity is the unitless parameter that describes how efficient real things are at radiating energy, right? So if we look at how it's defined, so epsilon lambda up there at the top, we have the spectral excitance of a real object at a temperature T over the spectral excitance from a black body at the same temperature. So if you remember with spectral reflectivity, we said spectral reflectivity is the amount of light reflected from an object over the amount of light which landed on the object. Right? So to compute reflectivity, we were relating the energy reflected by an object to another amount. Right? We were normalizing it by something else, and we normalized it by the energy which struck the object. Here we're going to normalize the energy which left a real object by a standard, and that standard is the energy that should leave a black body at the same temperature. Right. So if we just plot that up. So let's look at the bottom one first. So we have spectral radiant excitance, which is m lambda, right? And you've seen this stuff before. That curve should look familiar, right? That 6000 K black body curve should look pretty familiar. We have radiant excitance going up to 10 to the 8, and then we have wavelength out here. If I solve Planck's blackbody radiation law, and I assume the emissivity of 1, then I get this black curve, right? Now, if that was a real object that just happened to have a really, really high emissivity, I could calculate its emissivity, right? I would take this curve at any wavelength, and I would put it on the top line of this equation, right? And then beneath it, I'd say, well, that black curve is the amount of energy radiated from a real object at 6000 K. And I don't need to do all wavelengths, I could just pick one wavelength, right? Because it's a spectrally dependent term. And then say, well, the black curve is my measurement of the radiance from a real object at 6000 K. I then say, well, what's the black body radiance at 6000 K? And I just compute it using Planck's law, right? I just put 6000 Kelvin in, and I compute it. Now, that would give me the same curve, right? I'd get another black curve, which would be exactly the same as this black curve, right? So when I divided two black curves which are the same, that would just be 1, right? At every wavelength it would be 1, because I'd be dividing a black curve by an identical black curve. And that would give me the emissivity, so when I plot that, I get that chart up on the top, right? Which shows me the emissivity of a black body is 1, and it's 1 at all wavelengths. Now let's go to this case, the grey body curve. So imagine I have a target which I know is at 6000 Kelvin, right? Because an astronaut went down and measured it and it was at 6000 Kelvin. But I measured the spectral excitance coming off it, and it was this grey curve, right? So instead of peaking at about 10 to the 8, it peaks at about 10 to the 7. So in this case, I would say, well, this is my real body at 6000 Kelvin. So at any wavelength, I would put this value in the numerator of this equation, right? And I would then say, okay, it's at 6000 K. How much would a black body radiate at 6000 K? And I would put that in the denominator. And then I would divide one by the other. And I would get this curve here, the grey body curve, which would tell me the emissivity of that grey body was 0.1, which is about 10%. Most things in nature aren't grey bodies or black bodies, they're what we call selective radiators. So quartz, calcite, all of those rocks that you might want to fingerprint on planets, they don't have grey body spectra, they have selective radiator spectra, which means the emissivity is high at some wavelengths and low at other wavelengths, right? Like the quartz spectra that I showed you. And remember, the wavelengths at which emissivity is low or emission is impeded is the wavelength at which the material is characteristically absorbing photons because of its chemical composition. Right. So if I just do the same thing, what I'm really doing here is I'm taking the red curve, which is my selective radiator, which tells me, okay, this is at this wavelength, this is the amount of energy radiated by my selective radiator. At this wavelength, this is the amount of energy radiated by my selective radiator. If I want to work out the emissivity of that target, what I have to do is put the red curve over the black curve, and in that case, I get this red curve here. So just look at the red curve. I mean, this is fake. This is just made up stuff. But the selective radio looks like one of those real materials, right? I have peaks and troughs in my emissivity spectrum. If we look at this wavelength at about 2 microns, my selective radiator behaves almost like a black body, right? It radiates almost as much as a black body at the same temperature. Which makes sense because it does radiate almost as much as a black body. Because at those wavelengths, the red curve lies on top of the black curve. The wavelength at which my selective radiator is least like a black body is here, about 10 microns, right? Because the emissivity is down close to 0. And that makes sense because here is the minima in the energy emitted by my selective radiator. Right. So do people just see how you derive emissivity? Right. You take a real world material that you care about and measure the amount of energy it emits at a certain temperature, and then you just compute the black body flux at the same temperature, divide one by the other, and that gives you the spectral emissivity. So this is just an example. Quickly did this in the lab a few years ago. So that's a lump of quartz that we keep in the oven, right? And the oven's set to about 70 degrees C, I think. These are for just 300K. So yeah, this was at room temperature at the time. So lump of quartz at 300 Kelvin. I put an instrument and measured the amount of energy it radiated at a whole bunch of different wavelengths. And that was the red curve. Right? So this was the spectral radiance at a bunch of wavelengths I measured from that lump of quartz at a temperature of about 300K. So Christiansen frequency, the Strahlen band. This is where the quartz behaves kind of like a black body because it's close to a black body spectrum. This is where it doesn't. I then plotted up the spectral radiance from a black body at 300K, same temperature. And when I put that over that, I get this, which is the emissivity of quartz. So, is there anything mysterious about emissivity? Planck's black body radiation law describes the emission characteristics of black bodies. Things in nature, in reality, are not black bodies. Right? In reality, things are much less efficient at radiating energy than black bodies. And because things are made of different atoms and ions lumped together as different molecules, the wavelengths at which they are less efficient than black bodies varies depending on the chemical composition of the material. And that's why we have troughs at different wavelengths. To work out the emissivity, we would measure the emission from our real object at a temperature and then normalize that to the black body flux at the same temperature and just divide one by the other, and that's how we compute the emissivity. Okay. Anything mysterious about that? People happy? In the long wave, emissivity is the same as reflectance in the short wave. It's just the squiggles that encode the chemical information. Okay. Again, the troughs are where the interesting stuff is happening because it's at those wavelengths at KD in Beer's law, the all-important Beer's law. It's at those wavelengths that the absorption coefficient is high. Right? When photons try and travel through that material at those wavelengths, they are gobbled up really rapidly.
So it's saying like at that specific wavelength, it's 40% of what a black body would be emitting?
Yeah.
Okay.
Yeah, 40% is efficient.
Mm-hmm.
And then on the top curve there, you can see where the curves overlap, it's basically exhibiting black body behavior. It could never be higher, right? Because it couldn't emit more than black body because that would be impossible. Sometimes when you make these measurements, it's a little bit over 1, but that's just the experimental error, that's just noise in the sensor, whatever. Now, the way you do that for real is you don't just like hold around a lump of rock and make measurements of it. This is an instrument that Schwei has just over the corridor, actually, one of my faculty members. Again, you take a rock or a crystal or a mineral that you care about and you grind it up into a fine powder. And then you put it in here, which is in here. And there's a couple of ways that you can do this. Some labs have a setup where you grind up the mineral into a powder, you put it on a stage, and then you heat the stage, right? So you will warm that powder up to 400 degrees Kelvin, right? And then you will measure the amount of energy radiated from it, and then you'll just divide it by a blackbody spectrum at the same temperature. And in that way, you could compute an emissivity curve for that mineral. And then you could do that a million times with different minerals, right? And you could populate a spectral library. That's the most realistic way of doing it, because it really simulates what we do when we go around planets, right? On the surface of a planet, the sunlight heats the surface gets warmer, and it radiates a spectrum of light, right? So we're really, when we do that kind of setup, when we take a powder, grind it and heat it and stabilize its temperature and then measure the emission, then that's the most close analog to the real world situation. That's actually a bit of a harder setup, to actually have a heating stage that you temperature stabilize the powder and make sure it's uniform and it's equilibrium and things like that. The way people usually do it is using a thing called Kirchhoff's law. Has anybody ever heard of Kirchhoff's law? Right, so that's basically, it relates the reflectivity of a target to its absorptivity or its emissivity. And basically means that instead of measuring the emission from that powder, we can measure how much light it reflects. And then, assuming conservation of energy, we can just subtract the reflectance from 1 to give the emissivity. So what that looks like, and this is the way that Schrei's setup works over here, he shines light on the sample, measures its reflectance, and that gives us the red curve, right? Reflectance on this axis. He then just subtracts that from 1 to give the black curve, which is emissivity on this axis. And you can see they're just a mirror image of each other. So when you go into ENVI and you look at a spectral library and you see an emissivity spectrum in ENVI from a mineral out at 8 to 12 microns, almost all of them were derived using this technique, where they first measure the reflectance and subtract the reflectance from 1 to yield the emissivity, because it's just an easier way of doing the measurement. So just some examples of what it's looked like. So again, spectral radiant excitance. For a black body at 300 Kelvin is the black curve, which I just compute from Planck's law. And then the red is water at 300 Kelvin, which is a measurement, right? So water actually behaves very close to black body behavior, right? You see, the red curve is really, really similar to the black curve. It's just a little bit below here. And if we divide red by black, we get the emissivity of water. And we have this curve, which isn't that different from a black body curve, right? So we would call water's a grey body, which has nearly black body performance. We take peridotite, which is, in gross terms, the mineral which comprises most of the Earth's mantle. Nearly all of the Earth's mantle is made of a mineral, a rock type called peridotite. This is the amount of light that peridotite radiates in red, if it was at 300K, so that's how much energy it would emit. Black body at 300K, which is just the same as the curve here, I divide that by that, and I get this curve, which is the emissivity of peridotite. Right? Peridotite is least efficient at radiating energy at about 11 microns, which means whatever peridotite is made of is really good at absorbing energy at about 11 microns, absorbing photons with an energy of about 11 microns. Again, think Beer's law and the absorption coefficient. Granite is a rock which isn't that common on the Earth's surface, but it's an important rock that people try and find in planetary environments. You can't make granite without the presence of water, right? People think they have found granitic-like rocks, lots of them on the surface of Venus. If such rocks exist on the surface of Venus, they could only have been formed in the presence of large amounts of water, which would mean Venus was kind of warm and wet early in its history. So that's a big part of a NASA mission called Veritas, which was funded and then kind of cancelled, but I think will get funded again. A big part of it was to go and find granitic type rocks on Venus, because if they find them, then that shows that Venus had to have had water on its surface, because you can't make granite without water. So if we just look at granite, red curve is the amount of energy that granite emits at 300K divided by a black body. We get this curve here. Right. Now, I'll show you this on another slide. So the trough for peridotite is about 11 microns, right? The trough for granite is at about 9 microns. Right? So what that means, if we design a sensor to make measurements of emitted energy between about 8 and 14 microns, then if we had about 5 bands spaced across here, or 10 bands, we should be able to distinguish peridotite from granite, right? Because the wavelength at which they emit energy is very, very different. Right? We would just try and measure the wavelength of these peak absorption features, right? But again, what we're doing, we're measuring the emission, okay? So we just have to try and make measurements of emission across here, this wavelength interval, and in doing that, we should be able to distinguish granites from peridotites, right? Based on variations in the efficiency with which they radiate energy or their emissivity. Again, this is just a generic thing for quartz, but I've just put these things in so that people call this shoulder the Christiansen frequency, and then this band is called the Riststrahlen band, which is the absorption rate. But again, if you just look at these pictures, it's pretty simple, right? It's what a real object radiates divided by what a black body at the same temperature would radiate, and that gives you the emissivity spectrum. And our peaks and troughs are interpreted in just the same way as they are in the reflectance spectrum. Same kind of thing, transmission. I should change this and move it up to emissivity. These are basically emissivity spectra. So, as I said before in the last slide, granite had its trough at about 9 microns. Peridotite had its trough over closer to 12 microns. These are a bunch of silicate rock types from stuff that's like the Earth's mantle to stuff that's like the Earth's continents. And you'll see this Riststrahlen band moves to longer wavelengths as we go from granite down to this rock type dunite. Right? And all we're changing here is the chemical bonding in the silicon structure. Right? So that's why the long wave part of the spectrum is very good at distinguishing these rock types from each other, because the Riststrahlen feature in its wavelength is very, very sensitive to the way in which the silicon and the oxygen are bonded together. And then there's just a real world example. So this is the HiTi thing that we're delivering. I think we deliver it to NASA next, it's like the 4th of December or something like that. So we built one of these emission spectrometers that we're going to launch off the space station on a satellite. So this is some rock samples. So this is a lump of quartz, and then this is a Scotch cube. And then that's just a lump of rock I've got in my hand. This is an image. And then here's the spectrum of all of those pixels over there. And the unit should be familiar. Spectral radiance, watts per meter squared plus radian per micron. The quartz radiates much more energy at 10.5 microns and 8 microns than it does at 9 microns. Right? It isn't very good at radiating light at this wavelength because emission at this wavelength is being impeded because of the chemical composition of quartz. And that's why we have this emission trough here. And if I were to divide this curve by a black body curve, I'd get that curve. Right, so these are kind of model data. This is real data. But look, see that feature there? That double hump? That's that feature there. So that was it. I was just going to play around with this thermal camera for just a little while. People got any questions on this stuff? We spoke about Planck's law. We've gone through that a lot. We started the performance modeling thing in trying to work out how much energy would be available to us to measure in space from a target on the ground with or without an atmosphere. We then spoke about how there are a few ways that we can use thermal remote sensing data. One is just to work out the temperature of something, right? And if we want to work out the temperature of a target, a lava flow on Io, then we want to know the kinetic temperature We know we're just going to measure a brightness temperature. We need to know surface emissivity and transmissivity in order to correct our at-satellite signal to try and force our brightness temperature to converge on a true kinetic temperature, right? We then said how we can use day-night pairs of thermal image to work out things about thermal inertia, which is largely correlated with density. Or is it solid rock, or is it rock smashed up into grains? And then finally, we spoke about how the emissivity spectrum themselves are indicative of chemical composition, right? And all the physics and thought experiments is the same as they are in the reflected part of the spectrum, Beer's law, etc., etc. And we just described how you derive emissivity spectra from measurements of real objects versus blackbody standards. Okay. No question? Okay. So this is, I'm just going to put this on. Back in a second, we'll put a cap.
Picture
This
lecture this lecture is well put first.
Yeah.
So it ties things together. Okay, I'm gonna go look at new classes. I don't know. I didn't. Oh,
That's
I was
what I
busy.
thought Human Bite. I was so
I've never heard of that.
like, I was like, is he talking about Scotland or is he talking about like Scotland?
Scotland.
I don't know, man. Maybe a Scottish rock.
I know.
Okay.
I don't even know. I don't drink scotch. So.
Kind of cool because it's titanium, so it's really. This is really dark.
Where's the camera? Oh, it's back.
It's not.
Glasses look so weird.
That's even creepier. It's not a very flattering camera. I'll say that.
Oh, you got it.
Yeah, I got it.
I wonder.
Julia and I got it. It was a.
Oh,
I
I'm
didn't
sure all the other
recognize-
people will get it too.
No,
Oh, really?
actually,
Kiana isn't going because she's one of the.
so it's Julia, Athena,
Yeah,
Where
that's
we-
what I'm saying.
but
because
I don't recognize. I think Diana's in there.
Let me see if I
Recognize
recognize.
names.
I don't know
Is
her.
there anyone doing?
That's not our Taylor.
Oh, that's not our two?
I don't
I
think
think it
so.
is our
Taylor, is that her last name?
I don't know. I
I'm
just
not sure.
assumed.
Oh, that is our. I think that's our Diana. So it's mostly people from our class. Yeah, I'm sure Diana is the same. Let me look. I think it comes out.
It's gonna be 40 degrees.
I know. I have a.
Can't. Yeah.
My jacket
It's so
would be
cold.
too.
I have a puffer jacket. I have a big.
I have a down jacket because I was working up there before. but it's going to be huge for you.
Is that the thing you're talking to Peter about?
No.
Oh.
I'm going with the astronomy and astrophysics students. The seniors got chosen to go tour Keck at the top of Mauna Kea.
That's going to be
I'm a
really
senior.
nice.
You're technically a senior.
I'm past a senior. Yeah.
Well, aren't you graduating in like technically more than
I
you?
have over 100 credits.
Okay.
So I'm senior standing. If I had kept my history major, I would have been graduated last spring. But I have another. Or no, I would have been graduating this spring. I don't know. But yeah. I just have an extra semester. So I thought this was my last semester of my junior year. But I guess this is my first semester of my 3 senior semesters.
Wait, so okay. I guess you haven't taken enough credits for it to like do something weird at the end. But if you do 3 senior credits, wouldn't that like like the school would be confused by that? Because then you wouldn't have enough credits at the last semester, right?
No, I'm still taking 12 credits.
Are you
this
just taking
semester.
like an extra thing, or do you have a prerequisite that you need?
Alright,
It's just
so,
all my core.
This is a thing called Leslie's cube. A Scottish physicist, I guess, invented this thing. So you'll see it's a metallic cube. It's hollow. I just went and boiled a kettle of water and poured it in. Right. So the water was boiling, so it was about 100 degrees C. Okay. If I turn this thing around, you'll notice that it has a kind of two black sides, kind of vaguely scuffed up metal side, and then a side that's painted white. So this is a thermal camera. This is old. I think I got this in 2010 or 8 or something like that. So this is just like the ones that the cops use for finding, people running away from cars in the middle of the night and stuff like that. It uses there's an IR lens, and it uses a type of detector which isn't a photon detector. So we'll talk about this next week or the week after. There are two main classes of detectors. One is a photon detector, and we've spoken about that a load, right? A semiconductor where we have the valence band, the conduction band, and we're using the photoelectric effect to cause loosely bound electrons to join a current, right? The other type of detector is a thing called a thermal detector, which basically works a bit like a bimetallic strip. So basically, you have the similar thing, like it's an array with pixels, but each detector is a blackened metal flake that just absorbs light. And when it absorbs light, it heats up. And when it heats up, its resistivity changes. And what we do is we measure the change in resistivity across that blackened metal flake. So there are some differences, we'll talk about this next week. A photon detector kind of responds really quickly. As soon as you shine light on it, you'll get electrons being boosted from the valence to the conduction band. These detectors take a while, because you're shining heat on it, and it takes a while for it to absorb the heat, and a while for it to heat up, and a while for its resistivity to change, which means they just respond more slowly. The advantage is these things can be operated at room temperature. So the kind of photon detectors that I've been speaking about in the thermal part of the spectrum, you have to cool them to cryogenic temperatures. And to cool them, you need a fridge. The fridges are noisy, they vibrate, and they use a lot of power. So putting them on spacecraft is something that people maybe don't want to do, right? But these things just operate at room temperature without any cryogenic cooling, which means these things are cheaper. So I think when I bought this, it was about $30,000. If you were to buy one today, it'd probably be, about $50,000 with a thermal detector. You can buy the same camera with a photon detector, which is cooled, and the price will go up by an order of magnitude. It'll be $300,000 instead of $30,000, because the thermal detectors are more precise. But this will be good for what we're doing. So you can see I've got a temperature scale there. So that's somebody's face. Okay, so typical type thing, your water jug is kind of cool. Your hair is cold. Ears tend to be cold because there's not a whole lot of blood flowing through them, right? Same thing with people's noses. Tend to look cold, there's not a whole lot of blood flowing through your nose. Eyes tend to be weird. Glasses are certainly weird. Hair's colder, again, not much blood. As we're going around the room, these lights are a little bit warm. The casings of those lights over there are warm because they've been heated up. So again, this is just mapping. This is like a weird kind of color scale. But bright is hot, and then dark is not hot. Let's see if I can change that. Oh yeah. Okay, so that's like a rainbow palette, but similar thing. So if I point at this thing, I'll change the temperature range. telling me that's vaguely in sort of focus. So I'm looking at the black side now, right? And it's telling me that the temperature is kind of high, and it's telling me that the maximum temperature is about, it's above 70 degrees. Right, and it's variable because I've poured the water in, but the water isn't totally filled, right? So what I'm seeing here, what I'm measuring is a radiation temperature, right, or brightness temperature. The kinetic temperature, I don't know. There's a little hole on the top to put a thermometer in, but I've lost my thermometer. But this radiation temperature is less than the kinetic temperature of the water. Right? Watch what happens when I turn. Right. So the temperature of that side, the brightness temperature is closer to 20 degrees. Right. On the blackened side, that's like 75 degrees, right? I'll turn it around and show it this side, which is just aluminum, right? Kind of scuffed up aluminum. Then the brightness temperature is way down at 20 degrees, right? With a couple of these spots, which are much higher. But if you come over here and you touch that, you'll find that it's just as hot, right? The kinetic temperature of the metal is exactly the same. And it's kind of burning my fingers on both sides. But the brightness temperature of this face is way lower than the brightness temperature of this face. And that's because the emissivity of those two faces is very, very different. Right? This one is painted black. This face here is painted black. So it's like a half-assed black body. It's not a good black body. The one that I've got in the lab cost about $20,000. This cost me about $10 on eBay. But this is exhibiting close to the black body behavior. The paint is kind of efficient at radiating energy. The bare aluminum is not very efficient at radiating energy, right? So its radiation temperature is way lower, even though its kinetic temperature is the same. And then if we go to the white face, now you might think that the white face would have a very, very different temperature, but it kind of doesn't. Because it's white to our eyes, that doesn't mean its emissivity in the thermal part of the spectrum is different than the other paint. So the emissivity of this white paint is basically the same as the emissivity of this black paint in the thermal infrared, right? Their reflectivity is very different in the visible part of the spectrum, that's why they look white and black. But in the thermal infrared, they have very, very similar emissivities. It's only the uncovered face of bare aluminum that's a significantly different emissivity than all of the other painted faces. And you remember when we were in here with the spectrometer and we were looking at leaves and different types of paper. And I think if you remember, they all look the same in the infrared. Right? We were seeing changes in absorption in the visible part of the spectrum, which is why they look different colors, but all of the paper was kind of reflective in the infrared. Similar thing here, the emissivity wavelengths that our eyes can't see is the same for those different colors, which is why the brightness temperature doesn't change when I rotate from black to white. But the bare aluminum, and also these scuffs, and that's a bit of rust at the top there, are giving me very, very different brightness temperatures. So again, to change this, right, what I'd have to do is know what the emissivity of aluminum was between 8 and 14 microns, right? And if I knew that, I could correct that. Basically, that aluminum is not radiating as many photons as it should, given its temperature. To correct it, and of course, that brightness temperature, to get close to the true kinetic temperature, I have to have an estimate of just how poorly aluminum radiates. That's its emissivity, and if I know that, then I can work out the extra energy that should be emitted, add it, and cause my radiation temperature to converge on the kinetic temperature. But all materials are like that. They all lack the radiating efficiency of a black body, which is why we need to know that to do a lot of this chemical composition work.
Interesting.
Any questions?
And we're done. Thanks. I'll put this slide set on the landing so that you've got it.